Welcome to Presentation 26. Today I'm going to be talking about the display that has 240 by 320 pixels of resolution, and we're going to communicate with the displays via the SPI serial interface. I always like to start with our architecture. The display is in layer 3, and we're going to be using from layer 2 the SPI framework and the IO port framework. Now, today's agenda, I'm going to give you a description of the display. I'm going to present the data sheet. I'm going to talk about the display functionality. We're going to go through a couple of sample programs. And finally, we'll go through the summary. So let's start with the description. So as I noted, it's a 240 by 320 pixels of resolution. The display is a 2.4 inches in size. It's a TFT, and we're going to communicate with the display via the serial SPI interface. Now this is a picture of the front of the display, and I put a quarter so you can get an idea of the size. Next, here I'm showing the back of the display. Here where it says the TFT LCD controls, that's going to be our SPI control. Next, this display also provides touchscreen capability and SD card slot. Eventually, we'll go and talk about these two items. Now the display has a controller, which is the ILI 9341 controller. As you know, the controller is very important to figure out what is the number. As a matter of fact, this controller, when I bought it, I wrote this display, I should say, I wrote the controller number here, ILI 9343. Now, I wanted to show you here all the various controllers that we have. So when you buy your display, usually you should get, when you buy it, it should tell you what is the controller. But if you lost that information, then you can find out by, for example, looking at the size of the display. If your size is between 240 and 320 of resolution, then it can have this controller or this other controller. So you reduce the number of controllers that you could have to 2, and you can test it to see which one it is. If you have a 128 by 160, a 1.8 size displays, then probably your controller is this one, the ST7735. So anyhow, I just want to give you an idea of all the controllers there are out there, because as you know, the first order of business after you buy your display is to get your controller documentation. So let's go to the, I'll give you a flavor of the controller. The document ILI 9341 is the one we're going to use to get all the information we need to program our display. I will give you a global view, and so you can get a feeling for the document and also know where I got all my information from. So let's start by going to page 7, which is where we have the it shows the features and a little introduction. So here you have all the different characteristics of the display. And one of the important things to understand here, or to pay attention, I should say, is it says that it requires a 3.3 volts and also a logic of 3.3. That's going to become important when we start programming or hooking up our display to our microcontroller. So let's go to page 60. In page 60, it shows you how to connect your display to the microcontroller. And basically what you have is a SPI interface. So you have a serial communications via SPI. And here it shows you that you're going to need your MOSI, you're going to need your clock, the data command, and chip select. So of course we'll discuss that in detail once we get into the programming section. So now let's go to page 82. In page 82, what they do is they talk about the 16-bit parallel RGB interface. Basically, this is a color display, so we're going to have to send it the colors which is going to define what gets displayed. Next, let's go to page 83. Now page 83 is where they have a laundry list of all the commands, and later on they'll have a detailed explanation of each command, which I should say is very detailed and pretty good. Now I'm just going to pass through the pages of commands so you can get an idea how many commands there are and how much you can do with this display. And also I've highlighted the items, or the commands I should say, that I'm actually using or that we're going to use in our programs. The rest are going to be basically default. So here you can see 1, 2, 3, 4, 5 pages of commands. Now after the laundry list of commands, so you come here, you can see what commands are available, and then when you want to get the details, then you go to section 8.2, which starts with each of the details. Now there is a 1 page per command. You can see software reset. So I also mark the ones that I use, so you can see for each command there is one sheet. So let me go to one that I want to show you in specific, so you can see the amount of details that provides. So when you're going to place a character, or you're going to light up some pixels, the first thing you have to do is set up an area that says, hey, this is where I'm going to be working. So that's, to do that, you need to define the column and the page. So when you get to the command here, you can see how the amount of detail it has. So it tells you, hey, first send this command, then sends 4 parameters. That's going to give your X coordinates, and then send the next command, which is a passet, which is going to give you your Y coordinates, and it says sends 4 parameters, and then to conclude, so everything gets a store, send the 2C command. And basically the only thing, my only objective in showing you this is so you can get an idea of the amount of information, how rich this document is in details and in information. So based on this document, I'm going to create a I'm going to create a framework of all the commands, so we'll have them handy. So let's go and create all the extra framework we're going to need to make it easy to program this display. Okay, so let's go ahead and continue with the presentation. So as I noted, to be able to put my arms around all these commands, I need to create a framework so I can access them all. So how I create a framework is I did it as I've done it in the past. So the first thing we do, we enumerate all the commands to make sure we don't forget anything, so we can trace, and then we create a define for each of the commands. Once we've done that, then we can create the actual framework. So the framework in this case is going to be an include file, which I've called it framework LCD ILI 9341. So I'm going to include it in all the programs that we're going to write. Next, I mentioned that we need to use colors. There are standards for each color that defines each color. So the colors can be defined using 24-bit or 16-bit of resolution. So for example, black is all zeros, white is all Fs. Then you would have red, you have a value for the 24-bit, and you also have a value for the 16-bit. So what I'm going to do is I'm going to create two frameworks, one for the 24-bit resolution and one for the 16-bit resolution. So when I'm programming, I would call colors, not have hex numbers floating around that we don't know what color they are. So let's look at the framework. So we're going to have one framework which is called framework 16-bit color. And I'm going to have all the colors that I'm interested in. We have black, white, red, and the value. So in the program, for example, if I want blue, I'm going to call out the 16-bit the parameter bit 16 underscore blue. And I've done the same thing for the 24-bit. Okay, so now we know how to handle our commands. We know how to handle the colors. So let's look at the flow, how we communicate, how the controller communicates with the display. So we start, and the first thing we do, we're going to send a command. Next, follow the data. Every time we have a command, we have data associated with that command that follows. Then, as we're starting our program, the first thing we have to do is initialize the display. So we send commands data to initialize display. And we continue to do this till we've completed the initialization. Once we complete the initialization, then we go again to transmit commands, followed by transmit data. And we're doing this because we want to complete certain tasks. So we're going to continue to send commands and data till our task gets completed. Once that happens, then we stop. So let's see the code to do these things. So what I'm going to do I'm going to add something what I call chip select low and chip select high. So I have a line that goes between the controller and the display. If that line, which is called chip select, goes low, that means that I've selected the chip. I want to communicate with the chip. If it goes high, I am disconnecting from the display. Next, I need to tell the display whether I'm going to send data or command. And that's another line that I have with the display. So if the data command goes low, that means I'm sending a command. I'm right here. I'm going to send the command. If the line goes high, that means I'm going to send data. And finally, I have here how I'm going to reset the display. So I'm going to start with low, which is 0. Then I'll go wait a certain amount of time and then go high. So there is a sequence to do this, and I'll show you now. So let's see how it would work. So if I'm going to send a command, I'm going to have the routine that you send the command. Then, now don't forget that this is a serial ISP, SPI, I should say, interface, sorry. So I go in and I say data command, I'm going to go low, so that means I'm sending a command. Then I'm going to chip select goes low, that means that I'm selecting the chip. And the next thing follows the command that comes through this via to the routine. And then once I send my command, then I disconnect by saying the chip select high. Next, how I send data. So sending data is going to be similar to sending a command, except that the data command is going to be high, which means that I'm going to be sending data. And this is what happened. Port B goes positive. Then I send the data, and then the chip select goes high, which we're going to discontinue, which means the connection is going to be discontinued. Next, I have the TFT display reset. So I start, the display goes low, wait 20 milliseconds, display goes high, and then we're 150 milliseconds, and that's going to reset the display. Next, this what I'm showing here is supposed to be the pixels of the display. So I'm going to have in the X direction, which is this direction, I'm going to have 240 pixels. That was the resolution of the display, 240. So it's going to go between 0 and 239. And on the Y-axis, I'm going to have 320, which is the resolution. So the resolution of the display is 240 by 320. Of course, we start counting from 0, so 319 and 239. So now I want to write something into the display. So the first task is I need to define the area where I'm going to be turning on or off pixels. So how I do that? So first I need to define X0 and X1. Then I'm going to define the Y0 and Y1. So I'm going to send to the display this information, which gives me this particular area. And basically, I'm telling the display that I'm going to send you commands to turn on some of these pixels or all of the pixels. Now at this point, one of the informations that I need is going to be how many pixels are in this area that I've selected. So that would be x1 minus x0 times y1 minus y0. And when you multiply that, that would be 7 times 3, 21. So there are 1, 2, 3, 4, 5, 6, 7 times 3, 21 pixels. Okay, so now let's look at the code that will accomplish this. So we have a routine, and now I'm going to send it the value of x0, y0, x1, and y1. The reason this is a word of 16 bits is because, for example, in this case we have 390. The y can be as large as 319. If I had only 8 bits, then I could only go to 255. So I go here, all of them are 16-bit words. So the first item I do, and don't forget, like I showed you, I explained it. We go command data. So the first is a command, which is called cassette. And that tells it that I'm going to define the columns. 1, 2 columns. So take the first column, take the column x0 and send the most significant 8 bits first, and then the least significant bits. Then take x1 and do the same. So that takes care of my x0 and x1. Now I have to do the y0 and y1 to be able to define the whole area. So the command is pass it. So I send y0, the 8 most significant bits, followed by the least significant bit, 8 bits, and then I do the same thing for y1. After I completed both of these commands, then I send the 0 to C, which is the memory write. That means, okay, I'm done. Now store it in RAM. So you're going to use it. Okay, at this point, we have our area selected. So now we need to turn on and off pixels. How we do that? Okay, this is a snippet of how we would do it. So first we go, data command goes high. That means that this is data, followed by the chip select. So we're going to select. Now these two things happen really in parallel because they are two separate lines. So now I want to, let's assume I want to turn only 6, 7 of these pixels. So what I would do, I would go I equal to 0 and the window area would be 7. So in that case, I would light up only this. Now, if, for example, I decide my window area, or I'm interested for my window area to be 14, then I would put 14 here, and I would have these 14 pixels come on. Now, finally, if I decided what I'm usually going to do, is you calculate the area, and then you go to this loop, the number which is 21 times, which is the area or the number of pixels. Now, the data that I'm sending is actually the color that I want the pixel to be. So in this loop, I send the most significant bit of the color because the color is a 16-bit word. we're using the 16-bit resolution color. So we send the first 8 most significant bits, and then we send the 8 less significant bits. And once we're done with that, we've turned all the LEDs with a particular color. Then we set the chip select to high, which disconnects. So you select the area first, and then you start sending data, which is the color that you want each of the LEDs the pixels to come on. And as many times as you go, this is just going to keep going according to how much data you send it. So let's look now at display character. So what we have here, so far we know how to select an area and turn on and off pixels. So let's assume we want to write this ASCII character, which is an A. Now, I made a presentation where I showed you how we put this together. So the idea here is I'm going to start, I need to call out 1, 2, 3, 4, 5 words. It's going to take me to write the A. And each word has 7 bits. So I'm going to take the first word. If I have a 0, then I do nothing and I move to the next place. Then if it's a 1, I'm going to turn in 1 or many pixels, because I need to decide how many pixels are going to represent each of these boxes, which eventually gives me the font size actually. So I'm going to continue through this whole column. So when I'm done with the column, so I'm increasing y here, y plus 1, y plus 2. So I keep increasing y. So once I'm done turning all the pixels associated with this column, then I go to the next column, which is moving the x to the next place, and I have to bring the y up here again, and then I do this word. Then again I move the x to the right and start with the y again, and I do this till I get to the end. So let's look at the code, how we accomplish that. Okay. So the input to create this particular character is going to be the color that we want those pixels to be. So it's a 16-bit color. Then we're going to say the location where we want this letter to start, or this character. So initial X, initial Y. Then we're going to send the value, the ASCII value, which is these items. And finally, we're going to send the size. The size is going to be related to how many pixels I want to turn on when it's supposed to be on, or how many pixels I have to skip. Because if this is 0 and I'm going to turn this thing on, I need to skip to the next location. Okay, so I have something called mask. So when I get this word, what I need to do is evaluate each of the bits to see if I need to turn on pixels or do nothing. So what I'm going to do is I'm going to AND each of the words to hex 1, 2, 4, 8, 10, 20, and 40. And what that's going to do is going to let me know whether or not I have a 1 or a 0. So let's figure out how I do that. So I have a variable called a 1 0, which is if I find a 1 I'll make it a 1, otherwise it's going to be a 0. Then I'm going to have here X and Y, which I'm going to store the input values. So let's get started. So first we have the first loop is go between 0, starts at 0, and it's going to go all the way to 4. So that would be 5 words. 0, 1, 2, 3, and 4. That's basically what I'm going to do is I'm getting each of these columns, each of these words. Next, I'm going to have a loop that goes between 0 and 7. Basically, that's going to be, I'm going to grab each of these bits. 1, 2, 3, 4, 5, 6, 7. So how I do that is I have my mask, and then I have the actual word. So I have the ASCII value, and this is the first word because it belongs to this first word. So when I mask this, if it's true, that means that I have a 1. If it's false, I have a 0. So this is going to, from here I'm going to extract each of the bits, whether it's 1 or 0. Once I do that, I'm going to have this switch for the case 0 and the case 1. So let's look, for example, the first one is 0. So I go to my first mask, this is 0, so I have the case of 0. So basically, this is a do nothing, but I have to go to the next location, which is right here. So what I do is say y is going to be equal to y plus the size. Minimum size is 1, so I'm incrementing the size by 1 at least, and then I break. After I break, I go back to this loop. In this case, J remains the same ASCII value, and now we're going to go, and Y becomes a 2 because now I'm masking the second bit. So I'm going to go. Let's look at this. Let's look at the second bit. So the second bit here is going to be a 1. So the 1 or 0 turns out to be, has a value of 1. It we're going to be the case 1. So the first thing we do here is we set our area. So the area is going to be x comma y comma x plus 1 y plus 1. And then we do the data command. This is as we've done before when we turn the area. So we have an area, then we go follows the data. So we have, it's going to be high because it's data, and we select the display, chip select. And now we have to figure out how many times we have to loop to fill up the area we selected. So I decided that it's going to be four times the size. So we're going to start with at least turning on an area of 4 from 0 to 3. So each of these squares, when it's at 0, it's going to skip 4 pixels. If it's at 1, it's going to turn on 4 pixels. Sorry. And then we have the color that came in here as part of the display character. So we light up the 4 pixels, and then we disconnect from the display, chip select high, and then we increase the Y plus the size. So we keep going this way. Till we're going to do this till we've completed the whole word, extracting all the bits. At this point, we go x is equal to x plus size. So this is x, and we come up to this new x. And then the y that was here goes all the way to the top. And then we're going to do the same thing again for this other word. And then we'll go word by word till we're done. Okay, so at this point, we're ready for our first example. So let's look at the schematic. So we have one line that is the clock. We have the MOSI, data command line. We have a reset and chip select. Now I have here a chip which is the 4050 in between, and it's a 5-volt input pulses level is down converted to 3 volts. Basically, you have to be very careful here. Otherwise, nothing is going to work. The display, sometimes they say, well, this is good for 3 or 5 volts. It works fine with 5 volts. Now your ATMEGA is 5 volts. But it seems that if you read the small text, they're going to tell you that even though the display can work with 5 volts, you need to down convert your pulses to 3 volts. So then you put this chip in between that does the job. Now, so what I use is, if this is, most of the displays are 3 volts. I mean, the ones that you hook up to or you buy in Amazon or someplace. So the 3 volts, I provide a 3 volt, and then I provide the shift level to 3 volts because your ATMEGA is at 5 volts. Okay. So let's look at what we're going to do on sample program 1. So we're going to take the display and we're going to fill it with color purple. Next, we're going to draw squares at the following coordinates and of the color that I'm stating here. So we're going to have one at this coordinate, which is going to be orange. So basically this is the left corner. Then we're going to have in this coordinate, which is the right corner, which is going to be white. Then we'll have one on the bottom left coordinates. And then we'll have one on the right coordinates. So you can see the 239, 319. So that's the idea. And then finally, I'll set up a square which is going to be black color. So let's look at the code to get this accomplished. As usual, I will first give you a global view of the program, and then we'll get into the details. So we have here a routine that's going to initialize the SPI, the serial communication. We have a routine to initialize the ports, routine to write through the SPI, a routine to send commands to the display, to send data to display, a routine to reset the display, routine to initialize the display, a routine to set the area where we're going to work or where we're going to be allowed to turn on and off pixels. We have a routine to fill in the whole display screen in the display. We have a routine which is going to fill up a specific area of the screens. And finally, we have the main routine. So let's go back and look at the details. So let's start by the include section. In the include section, the new frameworks are going to be the 16-bit colors, the framework for 24-bit color, the framework for the ILI 9341 controllers. So those are the three new, the rest are the same. Also, I added to the define, I added when we call out the TS low, which is chip select low, is going to bring that port to 0. And we do the CS high, is going to bring it up to 1. So what we're going to do is to go high or low on the chip select. Next, we have the same, but the DC, which is we're going to send data or command. So it's going to be going low, and that's going to signify that we're going to send a data, and then high is going to be a command. Then we have the reset low and reset high. There are conditions where we have to reset the display, and this is what we're going to use. So let me show you. I set low for command and high for data on the DC data command. So let's get into the first detail. So we have the SPI init. Now this routine, we do exactly what we did when we went to my presentation on SPI. There is nothing new here. Now the init port, basically all we do, we set the data command to output, that's the DC, and the reset to output, that's the RST. Now we have, the next routine is SPI write. That's same as what we saw in the SPI. We put the data into this particular register, and then we wait until the flag gets set, indicating that the transaction was successful. Now let's see how we send a command. So we first bring the data command to low. That means what follows is a command. Next, we select the display, bringing this to low. Then we send the command. And after that, we set the chip select high again. Now the next is TFT send data. So we're going to send data, and it's the same as sending the command, except that we say the data command goes high, indicating that to the display that what follows is data. Next we have the display reset, and that we just started low, wait 20 milliseconds, then we bring it high, and then we wait 150 milliseconds. What we're doing is following the sequence for resetting. So now here we are at the TFT init. Now the initialization, I showed you how many commands we had, and you could use many of those commands just to initialize and get different results on how things get displayed. So I took the smallest subset that I could. And basically what you need to do is select the smallest subset that you can to get something to work. And then you start playing around with the commands and parameters till you get what you want. Because don't forget, when you buy the displays, you don't know that much about displays, and you have to learn by doing. So here I have a software reset. turn the display off. Then I send the pixel format. Then the MDCTL, which is, I send it hex 48. That basically tells you whether your display is going to be portrait or landscape. Next, you have the spout, which is sleep out. So we send it off, so now we wake it up, and then we turn it on. So that's a minimum subset of commands to get it initialized, and it works. Now, what follows here is set the window area. So as I explained before, we need to set up the window where we are going to do the turning on and off of the pixels. So we set the cassette, that's ILS 9341 cassette. That name comes from our framework, but we have it right there. So we have cassette, which is for sending the columns. And what I do, I send first the most significant part of the word and then the least significant. Now the input are 16 bits, so I send the first 8 more significance and then the 8 least significance for the X0, and I do the same thing for X1, more significant and less significant. That took care of the X boundary. Now we need to do the same thing for the Y boundary. So I send the passet is ILI 9341 under PASET. So again, what I do is I send for the Y coordinate the most significant 8 bits, and then I send the least significance. Next, I do the same thing for Y1. And finally, I send the command to go ahead and this to take place, which is the RAM write, memory write. So that's how we set the window area. Now, I have a routine which is going to fill up the screen. And this is just a shortcut. So I start and I want the display to be certain color before I start doing anything. So the first thing is I set area. So my X0 and Y0, X0, Y0, it's going to be 0, started on the left top corner. And I'm going to go all the way to X239, which is my 240, because it starts counting at 0, 240, and the Y is going to be 319, which is actually 320 of the display, because we start counting from 0. So basically, I'm covering the whole display, the 4 corners of the whole display. So then I go set the data command to high, and then I select the chip. And so I set up the area. Now I'm going to fill up the area. So how I fill up the area, I have to go through a do loop, a for loop I should say, which is going to be 240 plus 320, 76,800. That's how many pixels there are. So what I'm going to do is I'm going to send the color which I want the screen to be displayed 76,800 times to light up every pixel. So I send on the color, I send the 8-bit, the most significant, and then I send the least significant. So the color that comes with as an input to this routine, but they actually are going to get the color by using the framework 16-bit color. And then once we've light up all the pixels, then we chip select to high, which means we get disconnected. So now the last routine here is going to fill a window area. So before we fill up the whole display, now we're going to fill up a particular area. So to do that, first way to send a color. And then we say we're going to give it an X0, Y0, X1, and Y1. Those 4 parameters select the boundary of the area. So let's do that. So now one of the things we want to do is we want to select an area and we want to fill the area. Now that area could be 3 pixels, 4 pixels, 1 pixel. We decide what is that area. So let's start by, we need to find out how many times we're going to go through these loops. So let's figure out how many times we have to go. So that's going to be X1 minus X0. And then I'm going to add a 1 because we're starting to count from 0. And then Y1 minus Y0 plus 1. And then when I multiply these 2 parameters, we're going to get the area. That's the window area. And that's what we're going to use here on the window area. So the first thing we have to do before we can fill it up with this loop, we need to set the window area. So we go ahead from the inputs that we got X0, Y0, X1, Y1. We send this, which sets up the area that we can work on. Next, this is going to be a data, and we select the display. So this is where our loop starts to filling up the particular area we selected, or the portion that we want to use. So in this case, it's going to be the whole area. So we're going to send colors. If you want something to display, we need to define what colors it's going to be. So we send the most significant bit of the color, and then we send the least significant bit. Followed by we deselect the chip. Next, we get to the main routine. So what does the main routine do? So it's going to initialize the ports, initialize the SPI, initialize the display, and then it's going to fill up the screen purple. So let me go to the output for a little second. So this is the output, but you're going to see the places where we're not going to do any activity. It's going to be purple, because at the beginning, all this was all purple. So we found purple. Next, we're going to fill the area between, we're going to color it orange first, 16-bit orange. It's going to be starting from 0. X is going to be 0. It's going to be 80. Y is going to be 0. And Y is going to be 100. And this is orange. So let's look at it. So 0, 0. This is 100. And this is 80. And the color is orange. Let's go to the next one. So in this case, what we're going to do is we're starting from 159.0. Then we have the next corner is going to be 239.0. Then we'll have 159.100 and 239.100. So let's see, and the color is white. So here we have the square that we color white. Now this is not quite white, but I think that has to do the picture I took with my camera. I have very good light. Next, we're going to do the blue. We started at 0 to 20. Let me go back. This is blue. 0 to 20. That would be 0, and this would be 220. And then we go 8319 with the blue. 80. So this is 80, and this is going to be the 319, which is the 320 of the pixel, no? We start counting from 0. With blue, then we have green and black, and it's most of the same. We have here the green, and then I place the square on black. So this is, anyhow, this gives you an idea of how to place squares on the screen, and that's going to be useful if you want to set, for example, buttons. You have different buttons you want to draw of different colors, and you know how. In our next sample, we're going to be able to put words into these squares. We'll have the capability. So anyhow, that's the first sample program, and let's continue with the presentation. Okay, so let's continue with another example problem. The example program. Okay. First thing we're going to do here is we're going to fill the display with color cyan. Next, in top of the screen, we're going to write "Hello World" in color black. Next, we're going to write all the ASCII characters between 32 and 133. Number 4, we're going to repeat what we did in 1, 2, and 3, but we're going to use a smaller font. So let's get into the programs. So hello world, all the ASCII values between 32 and 133. Then hello world again, and then all the ASCII value between 32 and 133, but we're going to use a smallest font. So let's look at the code. So I'll start by giving you a global view, and then I'll go back and only address the new routines. So here again we have the framework we added, the 16-bit color, 24 color, and the controller ILI 9341. We have our define, we set the data command chip select and reset, SPI init, initialize the port, SPI write, then send commands to display, send data to the display, reset the display, initialize the display, set window area, fill the screen, fill a window area. We have display character, so it's going to display one character at a time. We have write 2 by 2. It's going to write a string sending one character at a time to display character, and it's going to do it at a particular size, which I call 2 font size. Then we're going to have a write 1 which is going to be same as write 2 by 2, but it's going to be smaller font. Next, we have the main. So let me back and talk about the stuff we haven't, the new stuff, I should say. So the new is going to be display character. What this routine does is display one ASCII character at a time. So we have called something mask. And the purpose is to add each of these words, which the ASCII code to extract one bit at a time, whether it's a 0 or it's a 1. This is the parameter which is going to have it's going to be the 0 or 1. And then we have some temporary parameters, X and Y. So let's get going with this. So the first thing we do, we have an ASCII characters. So I've already explained this in detail during the presentation. So I'm just going to go a little bit faster here. So the ASCII character is formed by 5 words. So I have to get one word at a time. So this is how I do. ASCII 5 by 7. This is the ASCII value. And the J is going to be the first word of that ASCII representation. And then I'm going to end it with a mask. The mask 0 is going to get the first bit. So I mask, and then I ask, hey, is this bit a 1 or a 0? If it's a 0, that means that I don't need to turn on any pixels. All I have to do is go to the next place, next location. And then I get here and we go back. Then what happens if it's a 1? If it's a 1, what I do, I know that I have to turn something on. Could be 1, 2, 3 pixels, depends what is the size of my font, how I've decided how big is the font. So I set an area, and then I go, this is going to be high, which means it's data. Then I select the display, and then I have to figure out how many times I have to go through this loop to light up the pixels that I've decided. So it's going to be from k equal to 0, and I'm going to loop equal to this 4 times the size. So I always select, I like to turn on 3 pixels so you can see the words. Next, as before, what I do, I send the most significant 8 bits of the color, and then the less significant. Now I have a non-hex FF that's doing nothing, and I don't remember how it got there, but there it is. It's doing nothing. I'll eventually get rid of this. Next, after I've light up the correct number of pixels, then I disconnect from the display, which is chip select goes high, and then I break. So I'm going to do that for the first ASCII words. When I'm done, then I jump back here. What I do here is I move to the next column on the display, move to the right of the next column, and I start from Initial, and I start the same thing doing for the next column. So I do this for the seven words. So let's go to the next one. Here we have write string 2 times 2, string 2 times 1. So from the main, I'm going to get the color, then the size of the chart, then I'm going to get a string, and I'm going to get where I wanted to start writing that string. Now the size of the chart, I put it equal to 2, because basically it can be 1 or 2. So this size chart wasn't needed, but I put it there for future use. So we have size chart is going to be 2, and then we're going to do a while where we get our string, and we're going to display a character. We have a color, x1, y1, then the one character from the string, and then as soon as this is complete, we go and get the next one, and then we have the size. And then I increase the new x, where I want this new character to be written, is going to be at x size plus 12. That's how much space I need to keep the spacing for this particular size. And then I just grab the whole string. For the write one by one, it's the same, except that the size of the chart is 1. And I do exactly the same. And the spacing between the characters is going to be 6 pixels. So let's go to the main. So we're going to initialize the ports, initialize the SPI, initialize the display, and then I'm going to set 2 variables, x and y, to be 10 and 60. Then I will fill the screen calls cyan, wait 300 milliseconds, and then write the 2 by 2 hello world at the 40x20. That's where it starts. After doing that, the next thing I'm going to do is I'm going to send all the ASCII characters to be displayed, starting at 32 and going to 133. So I'll go display character. I want to be black. X is going to be 10. Y is going to be 60, like I defined it here. And then the J is actually the ASCII value, and it's going to be size 2. So one of the things that I do in this loop, before setting the next character, I selected x plus 20, I increase the distance, and then I say, hey, if x is greater than 200, let's go to the next row, and then increase 10. So basically, all this thing it does is make sure that we get to the end of the edge of the display, and we go to the next column. So we don't have a word that is half in one row and then half in the other row. And this is just by experimentation. I just put in some numbers so the display looks okay. Next, I do the same thing, sending all the ASCII character, but this time I do it with the size equal to 1, much smaller. And then again, I just keep the same distances until the whole thing, so to make sure we get nice, all the characters, there's enough space on the left and on the right of where I'm writing. So let's look at the outcome. So here we have the number 2 and number 1 size. So let me go back so you can see. You can see here the what I call the number 2 size is larger, and then I just kept some space and put the hello world and put a little bit of space, and then I go to the next set, which is basically the same space, but you can see the letter are much smaller. So the idea is that you're going to put 6 on the display, buttons and whatnot, and then you're going to write what they are. And so you use 2 different size of fonts. You can use this one, or you can use this a smaller size. So anyhow, that's the end of the second example, and let's continue with the presentation. Okay, so here we are, and what comes next is the summary. There was a lot of information that I provided, and I'm sure it's going to take to see this a couple of times to be able to digest this whole thing. So what I showed you, first I gave you a description of the display. Next we went through the data sheet, give you a high-level view of the data sheet. I talked about the functionality. And we went to a couple of sample programs so you get an idea of things that you can do with the display. So anyhow, I hope you've enjoyed this presentation, and thank you for taking the time for listening to me. So I'll see you the next time. Thank you again.